in our previous lecture, we introduced coupled inductors and the dot notation. And we had some examples to get familiar with those new concepts. And in this lecture, let's remember what they were, okay, on a simple example. So that would be a quick review of what we have seen last time. And then we will talk about concepts such as power and energy and initial condition models in coupled inductors. Okay. So our example is such that we will formulate a circuit, a dynamic circuit, in terms of mesh currents, okay, and that dynamic circuit contains a coupled pair of inductors. Okay, so let this be our circuit. We have two inductors and a capacitor. So this is a third order circuit. This is R1, R2, L1, L2, and they are coupled. C plus minus BC. Dots are placed in such positions, and M is indicating a mutual inductance between those coupled pair of inductors. And let BS denote the voltage of the independent voltage source. Okay. Now for this circuit, suppose we're given the following mesh currents already labeled I1, I2, and here for the third mesh we have I3, all in clockwise direction. So what we're going to do now is we're going to formulate the circuit in terms of mesh currents, meaning that for each mesh we're going to write KV out. We're going to sum up the voltages that we come across while we go along the loop and write them down. So, let's start from the first mesh. So we have mesh 1. Okay. So what we have here is plus minus this voltage, and then plus minus this voltage, and finally plus minus that voltage. This voltage, let's call it V1, the voltage of the first inductor, is the current L1 times rate of change of the current passing through L1. But since this inductor is coupled to the other inductor, this voltage depends also on the current passing through the second coil. Okay. Now, let this be the inductor current, okay? And since this is in the outer mesh and it doesn't touch any other meshes, therefore this inductor current is no other than the mesh current itself. Likewise, suppose that this is the direction of our second inductor current, and it's nothing other than the second mesh current. Okay. So therefore, what we have here is, for mesh 1, plus minus this voltage, which is L1 d I1, okay, plus or minus n times rate of change of the second inductor currents. Now let's determine whether this is a plus or minus. For that we look at the dots. This is I1 and enters from the dotted terminal. This is I2, it leaves from the dotted terminal. Therefore, the sign must be negative. And this expression is this voltage here, V1 plus minus. And then we have this voltage plus minus, which is R2 times the current passing through the resistor in this direction, which is I1 minus I2. Okay, and finally we have R1 times this current, which is I1 minus I3. And by KVL, this sum must equal to 0. So let's do the same thing in the remaining meshes, mesh 2. Okay, suppose that we start from this point. So this is our first voltage, plus minus. Let's call it V2. What's V2? V2 is L2 di2. Okay. Then we have the coupling term, which is plus minus N times di1, and then we have already determined the sign, so we have minus N di1. Okay, so it's this voltage plus minus. The next thing is this voltage, which is minus Vc minus capacitor voltage. What's capacitor voltage in terms of the mesh currents? Vc is Vc initial, whatever initial voltage is, plus 1 over the capacitance. Then you're integrating the capacitor current. Okay, so capacitor voltage is this plus minus, therefore the capacitor current is that. And what's that? It's I3 minus I2. I3 tau minus I2 tau d tau. Okay? And this whole thing is capacitor voltage. And finally, we have this voltage plus minus, which is plus R2 times I2 minus I1, and that equals 0. That's our second mesh equation. And finally, let's write down the third mesh equation. Okay. Starting from this point, we're going clockwise. The first voltage is plus minus this voltage, which is minus Vs. Okay, and then we have plus minus this voltage, which is R1 times I3 minus I1, and finally we have plus the capacitor voltage, which is here, plus Vc0 plus 1 over C. Okay, so this, let's take this 0, because here we took initial time to be 0, it's not really important. Okay, so let's put 0 here, so let's put 0 here. And we have I3 tau minus I2 tau d tau. Okay, this should equal 0 by KVL. Okay, so these are the mesh equations for this circuit, which contains a coupled inductor. Okay, so having remembered coupled inductors and the dot convention, now let's move on to new concepts. Okay, let's for instance talk about power and energy for coupled inductors. So suppose that this is our coupled pair of inductors, mutual inductance L1, L2, self-inductances, and let the voltage and current be labeled as follows. I1, and here we have I2. Okay, so the power of this 4-terminal device is simply the power of this coil plus the power of this coil. Okay, the second coil. By power, here we mean instantaneous power. Okay, product of the voltage and current. So let's write them down. instantaneous power of the first coil is, let's call it P1 of t, and that's I1 of t times P1 of t, because the power for a component on a branch is simply the product of branch voltage and branch current. Okay, now let's write this voltage in terms of the currents. So that equals I1 of t times V1 of t. What's V1 of t? V1 of t is L1 di1 plus n times di2. So L1 di1 t over dt plus n di2 t over dt. Okay? So that's our first power, and everything is now in terms of the currents. Likewise, power of the second coil, let's call it P2 of t. It's I2 of t times V2 of t. And let's also do the same thing here, I2 of t times V2 of t. What's V2 of t? It's L2 di2 plus n times di1. Why plus? Because of the dots. Both currents are doing the same thing. They're entering from the dots. So we have now L2 di2 t dt plus n di1 t dt. So this is P1, this is P2. You take the sum, P1 plus P2, and that's the instantaneous power of this 4-terminal device, the coupled inductor. So let's do that. Let's do the sum. So the total instantaneous power for this device at any given time equals P of t, and that's P1 of t plus P2 of t. So let's write that sum using the expressions that we obtained earlier. So P of t, therefore, equals L1 di1 plus n, excuse me, we have L1 I1 di1. Okay, so I forgot this term. So L1 di1, and then we have another I1 plus n I1 di2. Okay, so this is the power of the first coil. Likewise, we have L2 I2 di2 and n I2 di1. Okay, so that's the sum of 4 terms, the power of the coupled inductors. Okay. Now, remember that for the usual inductor and also for the capacitor, they were able to store energy. Okay, those dynamic components, capacitor and inductor. And when you have such a component, then this power, this power, has a physical meaning. It's simply it is simply the time derivative of the stored energy. Okay, so let's ask ourselves, what is this thing is derivative of? Okay, it's not difficult to see that this can be written as d over dt. Okay, time derivative of the following expression: 1/2 L1 I1 squared plus n I1 I2 plus 1/2 L2 I2 squared. Okay. Therefore, this thing here must be stored energy of the coupled inductor, because its derivative gives us the instantaneous power for the coupled inductor. So let's write our finding down. Hence, the energy stored, okay, or stored energy at any given time t depends only on the value of the currents passing through the coils at that particular time. Okay. W of t minus infinity to t, so that's the definition of stored energy. The integral of the power p tau d tau, and by definition everything is 0 at the very initial time, okay, which is represented by minus infinity. So that equals, therefore, this 1/2 L1 I1 t squared plus n I1 t I2 t plus 1/2 L2 I2 t squared. Okay. Now for the usual, just a regular single inductor, for the uncoupled case, what we did have was, we had this form, 1/2 L, the inductance times the square of the current. Now, for the coupled inductor, we have that term, we have also 1/2 L2 I2 squared term, but also we have the cross term here, n times the product of the current. So it looks a little bit difficult to remember this formula, but by a very nice rewriting of this, we will be able to express stored energy of a coupled inductor in a very elegant way. Okay? All we have to do is just realize that this can be written as the following: 1/2, okay, times this row vector I1 of t, I2 of t, times this 2x2 matrix L1 M L2, and times this column vector which contains the currents. Okay. Therefore, since we immediately recognize this matrix is the inductance matrix, which we were calling L earlier, and this is our current vector I of t. Therefore, this is no other than IT transpose. Okay, so hence we have obtained a very elegant form for stored energy in a coupled inductor, which is 1/2 I transpose L times I. Okay, therefore we can write this equals 1/2 I T transpose L IT. Now that for the single inductor case, this simply boils down to the stored energy formula that we have obtained much earlier in 201, which was 1/2 L I squared. But now, since we're dealing with vectors and matrices, writing 1/2 L times I squared would be meaningless, okay? Because L is now the matrix and I of t is a vector, and then taking the square of that vector is senseless, okay, grammatical. Okay. So we have obtained stored energy for a coupled inductor. And for passive inductors, that energy must or can never be negative, regardless of the current passing through the coils. Okay, so let's put that remark down. For passive inductors, and this remark we can take it as definition of passivity for coupled inductors also. For passive inductors, the stored energy cannot be negative. Okay, regardless of the current passing through them. And since, in principle, we can choose whatever current we want that would pass through the inductors, so that would mean one half Li transpose Li is never negative, always non-negative for all I, where I is the current vector. Okay, for all vectors, this expression, which is a scalar, okay, is never negative. Now, if this is the case, this matrix, note that I is our variable here, and this matrix L is fixed, it's constant, it's our inductance matrix. So, if this is true for all possible vectors I, then this must contain certain information regarding the inductance matrix L. In other words, we should be able to check passivity directly considering the inductance matrix. And the question is, how can that be done? And it's very simple to do that because L is a symmetric matrix. Inductance matrices L satisfying this condition 1, and here we're talking about the general case, not just for 2 by 2 L matrices, but for general n by n inductance matrices, are said to be positive semi-definite. Therefore, we have obtained a definition of passivity for coupled inductors in terms of the inductance matrix, okay, which is the following. A coupled pair of inductors, or in general coupled inductors, are passive assembler components if and only if the inductance matrix is positive semi-definite. Okay. Now here comes the question: how to check for a given inductance matrix, how to check positive semi-definiteness. In short, PSD. So what's a condition, mathematical condition, that will guarantee that a given matrix is positive semi-definite matrix. Okay. So L inductance matrix is positive semi-definite. This is the answer. Okay. Given inductance matrix is positive semi-definite if and only if, because this is symmetric, this condition holds only for symmetric matrices, if and only if lambda k L is non-negative. Okay, so this is these are the eigenvalues of L. Okay, so for symmetric matrix, to check positive definiteness, all you have to do is check the eigenvalues. If all the eigenvalues are non-negative, then and only then matrix of consideration is positive semi-definite. Okay, so having talked about stored energy and also passivity, now let's talk about another way of writing the terminal equations, okay, for coupled inductors. Now let's write terminal equations by putting the currents on the left-hand side. Okay, by which I mean using the integral form. Okay. Previously, what we had was voltage or voltage vector equals inductance matrix times the rate of change of the current vector. Now, what we want is we want current equals something. That something will be depending on the initial currents and also the integral of the terminal voltages, the port voltages. Okay. So suppose that we're dealing with this coupled pair of inductors, plus minus V1, plus minus V2, L1, L2. And now that the voltage is only dependent on the rate of change of currents. Okay, this is I1 and this is I2. Whereas the currents will depend on voltages, but not only on voltage, but also on the initial currents. So let's therefore give some name to the initial currents. I1 0 minus is called I1 0, and I2 0 minus is this I2 0, which is some constant, okay? 0 amps, 2 amps, minus 6 amps, something. So, to obtain the thermal equations in integral form, so let's write down the form of the thermal equation that we have already considered, namely V1 of t, V2 of t equals inductance matrix times rate of change of the currents. Inductance matrix was L1, N, L2, self-inductances and mutual inductance. And here we have di1, dt, and di2, dt, rate of change of the currents. Okay. Now, what we want is, from this equation, an expression for the currents, okay, I1 of t, I2 of t. For that, what we're going to do is, we're going to integrate both sides. So let's do that. Okay, so integrating both sides of this spectral equation, we have 0 minus to t v1 of tau d tau, and same thing for the second voltage v2 tau d tau. Okay, so that's the integral of this vector. Integrating a vector simply means integrating separately every entry. And then that equals, since it's a constant matrix, we can just carry it outside integration, and therefore we can write it exactly as it was in the first term of the equation. And then what we have is this matrix multiplying the integral of that vector. And the integral of that vector, since it's in terms of the rate of change of the currents, what we have here is I1 of t minus I1 0 minus. Okay, so that's the integral of the first term. Likewise, the integral of the second term is I2 of t minus the initial current. Okay, and this matrix here is what we're calling the inductance matrix L. Okay. Therefore, by throwing the initial condition terms to the other side, what we have is L times I1 of t, I2 of t equals L times the vector that contains the initial currents, namely I10 and I20. Okay. Plus these integrals, V1 tau d tau and V2 tau d tau. Okay. And now we're very close to be able to write I1 I2 of t. All we have to do is multiply both sides with the inverse of inductance matrix, provided that inverse exists. Okay. So assuming that it does, we have the following. When the inverse of the inductance matrix exists, we can write I1 of t, I2 of t, okay, or simply I of t as a vector equals I10, I20, because multiplying both sides with L inverse will cancel this L. You will be left with the initial condition, current vector only, plus L inverse times the integral of this vector V1 tau, V2 tau, d tau. Okay. And once again, integrating a vector simply means you're integrating every term separately, each entry separately. So this is I of t, our inductor current vector. This is I0, or I of 0 minus, which is our initial current vector. And then this vector here is V of tau, the voltage vector for the coupled inductor. Okay. Therefore, we can write this equation in more compact form and say I of t equals I0 plus L inverse 0 minus t V of tau d tau. Okay. This is the same form as the terminal equation for a single inductor. The only difference is that with single inductor we usually wrote this term as 1 over L, but now we cannot, because 1 over L doesn't make sense, because L is a matrix, no longer a scalar. Okay, so this is the terminal equation in integral form. Okay, now for capacitors and inductors, earlier we talked about the initial condition models, okay, which we said are sometimes useful when we want to express our dynamic elements without any initial stored energy. Okay, so usually inductor has an initial current or initial energy, likewise a capacitor has an initial voltage or initial energy, and when we put them on a circuit diagram, we have to write down somewhere that initial value, okay, initial current or initial voltage. And it's possible, we saw through initial condition models, that we can express or we can represent that component, the capacitor, let's say, by an empty capacitor, okay, and then somehow we have to express that initial stored energy in the capacitor through other means, okay, and that we saw is possible through independent voltage source or independent current source, and the dual case was also true for the inductor. And now what we're going to do is we're going to generalize that idea to the coupled inductor case. So let's do that. initial condition models. So this is how we usually represent our coupled inductors. Okay. Plus minus V1 plus minus V2 I1 I2 and here we write somewhere close to the circuit the initial conditions. I1 initial is I1 is 0 and something minus 6 amps, 2 amps or 0 amps, and likewise for the second quarter to 0. Okay, so this is how we represent the component usually. So let's call this representation 1. Okay. Now we're gonna obtain equivalent, or write down equivalent representations where again we have a bunch of inductors, coupled inductors, but this time those inductors will be without any initial current, or the initial currents will be 0. And then this information therefore has to be stored somewhere else, and that somewhere else will be independent sources. One way to do that is the following. So we say this 4-terminal device is equivalent to, from the point of view of voltage current characteristics, for all positive times to the following two other configurations. First configuration is, okay, let me squeeze it a little bit. Equivalent for T positive. Again, we have a pair of coupled inductors, and the parameters L1, L2 are the same. L1, L2, and also the mutual inductance. Okay, so let's call this current I1 hat, this current I2 hat. Okay, so those are the currents of these coils. Okay. And I hat 1, 0 minus is 0, and I2 hat 0 minus also 0. So initially there's no stored energy in the inductors. Okay. And by initial time we take 0 minus. But this initial condition should somehow express itself in this device, 4-terminal device, if we claim that there's an equivalence, and that we're going to do by this pair of current sources. Okay, so here we have an independent current source. Its direction is like that, and what it produces is I1 0 U of t, and here we have I2 0 U of t. U of t is our unit step function. Okay. And as for the voltages and currents, we have, this is I1, this is V1, this is I2, and this is V2. Okay. Now that I1 hat and I1, they are not the same current because of the sources, likewise for I2 hat and I2. And this further is equivalent to the following model. Again, we have no initial currents on our coils. And this time, the initial condition information will be stored in independent voltage sources with impulsive nature. Plus minus V1. This current is I1. plus minus V2. This current is I2. And the parameters are the same, L1, L2, and this L inductance M. And now how about these sources? They are independent voltage sources with polarity plus here minus here. And voltage is such that it's L1 I10 plus N I20 delta t. And delta t is our unit impulse function. And here we have L2 I20 plus N I10 multiplied by this. Okay. Here I10 minus equals 0, I20 minus equals 0. So initially, those two coils, those two inductors are without any energy, without any current. And similar thing is the case for the configuration 2. So let's call this model 2, and let's call this our model 3. And our claim is such that these three models, 1, 2, and 3, they are equivalent for T positive. And by equivalent we mean the voltages V1, I1, and currents V1, I1, I2, V2, and the same here and here, they all satisfy the same exact equations, the same relationships. We're not going to drive them, drive those. Okay, it's left as an exercise. All you have to do is just write down the terminal equation for calc inductor, and everything will follow from there. So let's put that as an exercise. Verify that for all configurations okay, 1, 2, and 3. Okay, 1, 2, and 3. The important thing about 2 and 3 is that in those coils we have no initial currents or zero initial current. Okay, so we have 4 positive times T positive following relationship L1 and L2 I1 of T I2 of T equals L1 and L2 I10 I20. Then we have the integral term E1 tau V2 tau d tau. Okay, so that since they all satisfy the same current voltage relationship, we can use this notation. They're equivalent. Okay. So that's about it, about the couple inductors. So let's therefore conclude with an example, an numerical example. Here is our example. Consider the following circuit. Okay, where we have 3 inductors and a resistor and voltage source. Voltage source is sinusoidal, oscillating at 3 radians per second frequency. Okay, it's cosine 3t, the magnitude is 1. And here we have 3/4 ohm resistor. And these two inductors are coupled. 2 Henry is the mutual inductance, 1 Henry is the self-inductance of the first coil, 6 Henry is the self-inductance of the second coil. And here we have 1 Henry for this coil, which is not coupled to the remaining, to the other inductors. And two voltages are labeled as follows. This is V1, and here we have the voltage of the 1 Henry inductor. Okay. Now, assume that all the inductors initially are without any stored energy or without any current. Okay. Assume zero initial conditions. Okay, so the question is find V1 and V2, these voltages for T positive. Okay. Now here we have three dynamic components. Although the circuit is second order, but still we will be able to obtain the answer, this voltage V1 and V2, by using only first order circuit theory. Okay, we're going to solve this problem using very simple steps. Okay, so step one is, or could be, the following. Okay, we're gonna combine those three inductors into a single equivalent inductor. Okay, it cannot be done always, but in this case it can be done. Okay, because there's nothing, no resistor or something capacitor pollutes the topology. Okay. So step one, therefore, is find equivalent inductance. Equivalent inductance, where? Equivalent inductance here. So plus minus this voltage is V1. Let's also do some labeling with the currents 1 Henry, 6 Henry. This is V2. Okay, so let me call this current I1. Okay, so what we're hoping to find here is we want to be able to obtain an expression where V1 equals something times the I1 dt. If we can do that, if we can achieve such an equation, that something will be the equivalent inductance, okay? Seen from this pair of terminals. And then by that equivalent inductance, we can just replace this bank of inductors with a single inductor, and then we have a source and a resistor and a simple LTI inductor connected in series. That's the first order circuit. We know how to solve it. We can obtain that, and we can obtain V1. Okay, we can solve that and obtain V1. And then once we have V1, we can figure out perhaps V2, and then we will have solved the problem. Okay. Now the question here at this point is the equivalent, finding equivalent inductance. So let's do that. So this is I1, this is V2. Let me call this current I2. That's the current of the 6 Henry inductor. And let's call this current also something. So suppose this is our first inductor, this is the second inductor, so therefore that's our third inductor. Because it's our third inductor, I'm going to label that current as I3. Although there's really not much need, because I3 is simply minus I2 due to KCL. Anyway, So let's write down the terminal equations. And from those equations, we're hoping to get V1 equals something times di1. So what we have is V1 equals L1 di1, okay, plus M di2. Okay, so that's the terminal equation for the first coil. For the second coil, V2, we have L2 di2 plus 2 di1. That's the second terminal equation for the coupled inductor. And finally, we have the terminal equation for the uncoupled inductor, which is V3, the same as V2, because we have parallel, equals what? L times, or L3 times di3. Okay. And what's I3? I3 is minus I2, therefore V2 equals minus di2. Now V2 equals minus di2, V2 also equals that. Therefore, using those two equations, we can obtain a relation between di1 and di2. So let's do that. This implies that di2 equals minus 2 over 7 di1. So let's call this equation 2, whereas this is our equation 1. Okay. And then combining equation 1 and 2, we can get rid of di2, and then we obtain V1 only in terms of di1. That will give us the equivalent inductance. Okay, 1 and 2 implies V1 equals di1 plus 2 di2. di2 is minus 2 over 7 di1, therefore we have minus 4 over 7 di1, which makes 3 over 7 di1. Okay, therefore L equivalent or effective equals 3 over 7. Remember the units Henry. Okay. So that completes step 1. Let's move on to next step. Step 2. Okay. Now what we do is we remove the inductor bank, which contained 3 inductors, with a single inductor with inductance is 3 over 7 Henrys. And when we do that, the circuit all of a sudden becomes a very primitive first order LTI. This minus V1, this is our equivalent inductance, 3 over 7 Henry, that we computed in the previous step. And this current is our I1. Cosine 3t volts. Okay. Now, let's obtain the differential equation. What we have is di1 equals, okay, v1 equals 3 over 7 di1, therefore di1 equals 7 over 3 v1. That equals 7 over 3 times, what's V1? V1 is this voltage minus the resistor voltage, okay, which is 3 over 4 times I1. Cosine 3t minus plus minus this voltage, which is 3 over 4 I1. Therefore, we have di1 plus 7 over 4 I1 equals 7 over 3 cosine 3t. So what we're having here is a first order non-homogeneous LTI differential equation. It's non-homogeneous because the right hand side is non-zero. Okay. And also the initial condition is 0 because all the initial currents on the inductors are 0. Okay. Now we know how to solve this. Because the right hand side is non-zero, what we have is homogeneous part and particle part. Homogeneous part only depends on the natural frequency, which is minus 7/4. And the particle solution has the form same as the form of the input, which is a sinusoid at 3 radians per second frequency. Okay. Then we're going to combine those two pieces and apply the initial condition constraint to figure out the unknown. So, the homogeneous part has the following form: some constant to be determined later, and e to the minus 7/4t. The natural frequency of this first order circuit is at minus 7/4. Okay. And how about the particle solution? Particle solution has the following form: a cosine 3t plus some other constant sine 3t. Okay, so we have three unknowns, a, b, and k. To figure out a and b, what we do is we take this particle solution and put it into the differential equation. Since it should satisfy the differential equation, it will immediately give us a and b. Once we have a and b, what we do is we combine these two, IHT plus IPT. That's our overall solution, and that overall solution is subject to the initial condition constraint. And by applying the initial condition constraint, we find K. Okay. So, what we have therefore is I1 of t equals a cosine 3t plus b sine 3t. In this problem, I assume that we know what a and b are. Okay? By applying IPT, this can be to the differential equation. We can find what a and b are. So the a and b are known, and then plus IHT is this plus k e to the minus 7/4t. Apply that to that initial condition constraint, and that will give you k equals minus a. So therefore we have minus a e to the minus 7/4 t amps. So that's the current I1. Once we know the current, we can easily compute the voltage because it's 3/7 times its rate of change. So V1 of t equals 3/7 di1 of t, which is 3/7 minus 3a sine 3t plus 3b cosine 3t plus 7/4a e to the minus 7/4t. Okay. Volts. So that's V1 of t, which was one of the things that we were asked. The other thing that we were asked was V2 of t, which doesn't exist in this configuration, so we have to go back to the original configuration. Remember that earlier we obtained the following equations when we were writing down the term equations. We had V2 equals minus d I2, okay, and also we obtain di2 equals minus 2/7 di1. Okay. And when you combine those two, you have v2 equals 2/7 di1. Let's call this equation 3. Also, we have v1 equals 3/7 di1, so let's call this equation 4. Combine equation 3 and equation 4, that yields V2 of t equals 2/3 V1 of t. Okay. That means once we have V1, which we did already, okay, multiply that by 0.66666 and so on, and you obtain V2 of t.